I'm so glad you found your way here. Right now, beneath every snowflake resting outside your window, water molecules are quietly rearranging themselves, shifting, bonding, transforming without making a sound. You'll discover why frozen water never stays the same and understand how change is written into ice's very structure. Welcome to Get Sleepy Science. Even now, you're resting while somewhere on Earth, ancient glaciers are flowing downhill like rivers of stone. Snowflakes are transforming from stars into rounded grains, and ice crystals are growing new branches in the cold night air. Allow yourself to settle into this moment of quiet wonder. We'll discover 100 nature facts about snow and ice. From tiny molecular dances happening in each crystal, to massive ice sheets bending under their own weight, to the endless cycle of freezing and melting that shapes our world. These calm explorations of Earth's frozen wonders plant seeds of tranquility in restless hearts. Feel free to like and subscribe, or share a thought down in the comments. It helps others find their way here too, one sleepy soul at a time. Your presence here nurtures our growing forest of peace. Sink into your favorite resting spot. Allow your muscles to release, each breath growing softer. There's no need to remember these frozen facts. Just notice that warm, drowsy calm washing over you, like gentle snow settling on winter branches, each flake drawing you deeper into restful, effortless sleep. Close your eyes and breathe deeply. You're resting where ancient ice whispers secrets of eternal patience. Let your mind sink with winter's calm. And now we begin. Snow and ice appear frozen in time, but they're always changing. When you look at a snowbank outside your window, it seems completely still and permanent. Yet, at the molecular level, water molecules are constantly moving, shifting position, and rearranging their bonds with neighboring molecules. Even at temperatures well below freezing, this motion never stops. Scientists call this transformation metamorphosis, the same word used for a caterpillar becoming a butterfly. From the moment a snowflake lands on the ground, it begins changing shape. A delicate six-pointed star that took 30 minutes to form in the clouds might transform into a rounded grain within just a few hours on the ground. This endless transformation happens because frozen water exists very close to its melting point compared to most other frozen substances. Ice is, in a sense, always dancing between solid and almost liquid states. A snowflake's shape reveals its journey through the sky. Each branch, each arm, each tiny geometric detail formed in response to specific atmospheric conditions the crystal encountered as it fell. Temperature and humidity vary with altitude, so a snowflake falling from 30,000 feet experiences many different environments during its descent. When temperature hovers around 5 degrees Fahrenheit, flat plate crystals tend to form. At 23 degrees, the same water vapor creates long, needle-like structures instead. At around 14 degrees, you get those classic six-armed stellar dendrites, the intricate star shapes we picture when we think of snowflakes. Because each snowflake takes a slightly different path through the atmosphere, encountering unique combinations of temperature and moisture, no two snowflakes grow exactly the same way. Their shape is a frozen record of their atmospheric journey. The hexagonal shape of snowflakes comes from water's molecular structure. When water molecules freeze, they naturally arrange themselves in a hexagonal pattern, a six-sided geometric formation. This happens because of the angle between hydrogen atoms in each water molecule, which is about 104.5 degrees. When these molecules stack together in ice, they form a lattice structure with six-fold symmetry. It's similar to how oranges naturally stack in six-sided patterns at the grocery store, the most efficient arrangement for spheres. This hexagonal geometry is so fundamental that it appears in ice crystals everywhere, from the smallest frost on a window pane to the internal structure of massive glaciers. Even when snowflakes look irregular or broken, you can often still detect six-sided symmetry in their basic structure. The hexagon is ice's signature in nature. Recent research in late 2024 revealed that ice nanocrystals can form unexpected shapes. Scientists at several universities studying ice formation at the nanometer scale, smaller than 1,000th the width of a human hair, discovered that tiny ice crystals sometimes form decahedral and 20-sided icosahedral structures. These geometries form in ways that earlier understanding didn't predict, revealing that ice holds more secrets than scientists once imagined. The discovery helps explain why some snowflakes show unusual branching angles. These multi-twin nanocrystals form when water droplets just a few nanometers across freeze rapidly. While bulk ice always maintains hexagonal structure, at the smallest scales, ice can adopt more complex geometries. This microscopic insight helps explain patterns we see in everyday snowflakes. Even something as familiar as frozen water still holds surprises at the atomic level. Temperature determines whether snow crystals grow as plates or columns. Between 0 and -8 degrees Fahrenheit, ice crystals tend to grow as thin, flat plates. Between -8 and -12 degrees, they switch to growing as columnar structures, tall and narrow, like tiny pillars. Then, between -12 and -16 degrees, they return to plate growth again. This alternating pattern continues at different temperature ranges. Scientists have mapped these zones precisely through decades of laboratory experiments and atmospheric observations. The pattern exists because water molecules attach to ice surfaces differently depending on temperature. At some temperatures, molecules prefer to attach to the flat surfaces, making plates grow faster. At other temperatures, molecules prefer the edges, promoting columnar growth. This temperature sensitivity means snowflakes are remarkably precise thermometers of the air they fell through. Humidity affects how elaborate snowflake branches become. In very humid conditions, when the air is saturated with water vapor, snowflakes develop intricate, complex branching patterns, with delicate arms extending in multiple directions. In drier air, the same temperature produces simpler, more compact crystal shapes with less branching. Research by physicist Kenneth Librecht has documented this relationship extensively. He found that the most ornate stellar dendrites form when humidity is high and temperature is around -15 degrees Celsius, about 5 degrees Fahrenheit. Lower humidity at the same temperature produces simpler plate crystals. This happens because abundant water vapor provides more material for crystal growth, and it also affects how quickly molecules can move across the crystal surface to find their attachment points. Humidity is like the paint supply for nature's snowflake artist. Once snow lands, it immediately begins transforming through a process called sintering. The moment snowflakes settle on the ground, their sharp points and delicate branches start to round off. Water molecules at the tips of branches have fewer neighbors holding them in place, making these areas less stable. Through sublimation, going directly from solid to gas without melting, molecules evaporate from the pointed tips and redeposit in the concave areas and junctions between crystals. This process minimizes surface energy, gradually rounding all the sharp features. Within hours, a newly fallen stellar dendrite becomes noticeably rounder. Within days, it might look completely different, a simple rounded grain instead of an intricate star. This transformation happens even in temperatures well below freezing. Snow is never truly at rest. Snow depth affects how quickly crystals change shape. In a shallow snowpack, just a few inches deep, snow crystals can transform rapidly because temperature differences exist between the warm ground below and cold air above. In deeper snow, the middle layers experience more stable temperatures and change more slowly. Swiss researchers studying snow metamorphism found that temperature gradients greater than about 9 degrees Fahrenheit per 3 feet of depth cause rapid crystal transformation. In very deep polar snowpacks, several meters thick, the temperature remains nearly constant at depth, and metamorphism proceeds very slowly. Some Antarctic snow crystals, buried under many layers, remain relatively unchanged for years. Depth determines not just how fast snow changes, but what kinds of crystal structures develop within the snowpack. Wind affects snow crystal transformation by mixing and breaking snowflakes. When wind blows across a snow surface, it picks up snow crystals and tumbles them through the air. This mechanical action breaks off the delicate branches of stellar dendrites, creating smaller, irregular fragments. These broken pieces become what meteorologists call graupel when they collide with supercooled water droplets and freeze together. Wind-affected snow tends to be denser and more uniform in crystal size compared to snow that falls in calm conditions. In polar regions, wind-driven snow can remain suspended in the air for long periods, giving crystals more time to collide and break apart. The resulting snow creates harder, more wind-packed surfaces. Wind turns delicate snowflakes into something more like tiny ice pellets. Recent satellite observations of Antarctica's ice sheet reveal that surface melt patterns are changing. During the 2024 to 2025 melt season, Antarctic ice experienced above-average melting in December and January, with some areas recording over 30 days more of surface melting than the long-term average. The Larsen Sea ice shelf area exceeded average melt days by approximately 10 days, while the Amory ice shelf's eastern side showed increases of more than 30 days. These observations help scientists understand how ice sheets respond to atmospheric warming. Melt extent then declined quietly by early February, when temperatures cooled, showing ice's responsive nature. This variability shows that ice transformation doesn't follow a simple linear pattern. It responds dynamically to changing conditions, sometimes in unexpected ways. Pressure causes ice to deform in surprising ways. When ice experiences stress, from the weight of overlying snow or from gravity pulling it downhill, it doesn't break like most solid materials. Instead, it flows. Glaciers move downhill, not because they're sliding on water, but because ice crystals deep within the glacier slowly deform under pressure. Individual water molecules break bonds with their neighbors and form new bonds, allowing the entire mass to change shape. This process is called plastic deformation, or creep. Recent studies show that ice deformation happens through intermittent bursts rather than smooth flow. These dislocation avalanches occur when many molecules suddenly shift position simultaneously. Ice flows like an extremely slow river of stone. Glacier ice can be more than 100,000 years old at its base. As snow accumulates year after year in places like Greenland and Antarctica, older snow gets buried deeper and compressed into ice. The weight of overlying layers gradually increases, squeezing out air bubbles and increasing density. Ice cores drilled from deep within the Antarctic ice sheet contain ice that fell as snow during the last ice age. Yet even this ancient ice continues to deform and change shape under pressure. The oldest ice doesn't remain in its original position. It flows slowly toward the coast. Along the way, crystals grow larger through recrystallization, and the ice texture changes. Even 100,000-year-old ice is still transforming. Temperature gradients within snowpacks create unusual crystal structures called depth hoar. When the ground beneath snow remains near 32 degrees Fahrenheit, while the surface is much colder, say 0 degrees, water vapor migrates upward through the snowpack. This vapor deposits on the bottom of upper crystals, creating cup-shaped or faceted crystals that look nothing like the original snowflakes. Time-lapse images captured by researchers using CT scanners show this transformation happening over days. The resulting depth hoar crystals have weak bonds between them, making this layer unstable. In mountain snowpacks, depth hoar layers are a major cause of avalanches. Temperature differences invisible to our eyes create profound changes deep within the snow. Ice deforms faster at higher temperatures, even below freezing. Glacier ice at -4 degrees Fahrenheit flows much more slowly than ice at 28 degrees Fahrenheit. This temperature sensitivity helps explain why polar ice sheets move more slowly than alpine glaciers. Recent research at MIT, examining microscopic defects in ice, found that two mechanisms control ice flow: dislocation creep, where molecule-sized cracks migrate through the ice, and grain boundary sliding, where individual crystals slide past each other like cards in a deck. At colder temperatures, dislocation creep dominates. At warmer temperatures, near freezing, grain boundary sliding becomes more important. The balance between these mechanisms affects how sensitive glaciers are to warming. Temperature changes of just a few degrees dramatically alter ice behavior. Glaciers contain distinct layers that record past climate conditions. Each year's snowfall creates a layer that eventually compresses into ice. In polar regions where seasons are pronounced, you can count these annual layers like tree rings. Scientists drilling ice cores have created climate records stretching back 800,000 years. But these layers don't remain perfectly flat. As glaciers flow, the layers fold, stretch, and sometimes overturn completely. The original horizontal layers become curved and distorted. Satellite observations and ground-based measurements help scientists map these deformed layers. Understanding how ice layers bend and fold is crucial for correctly interpreting the climate information they contain. The ice remembers history, but in a warped and stretched form. Fresh snow reflects about 80 to 90% of incoming sunlight, more than almost any natural surface on Earth. This high albedo helps keep snow-covered regions cold, because most solar energy bounces back to space instead of being absorbed. But as snow ages and crystals transform from delicate dendrites to rounded grains, this reflectivity gradually decreases. Older snow might reflect only 60 to 70% of sunlight. Dirty snow containing dust or pollution reflects even less, sometimes below 50%. Climate scientists pay close attention to snow albedo because changes in snow cover create feedback loops. Less reflective snow absorbs more heat, melts faster, exposing darker ground that absorbs still more heat. Snow's changing shape affects Earth's energy balance. Meltwater refreezes within snowpacks, creating ice layers. During warm, sunny days, even when air temperature stays below freezing, solar radiation can melt snow at the surface. This meltwater percolates down through the snowpack until it reaches colder layers and refreezes. The resulting ice layers are much denser than surrounding snow. Over repeated melt-freeze cycles, these layers grow thicker. In spring snowpacks, you might find dozens of thin ice layers separated by snow. Each layer tells a story of a warm period, followed by refreezing. These ice layers affect water drainage through the snowpack and change its structural properties. The snow becomes stratified, with alternating layers of different density and strength. Ice crystals grow larger over time through a process called Ostwald ripening. In any collection of ice crystals, some are larger and some smaller. Water molecules tend to evaporate from smaller crystals and deposit onto larger ones, because smaller crystals have higher surface energy. This causes small crystals to gradually disappear, while large crystals grow bigger. In a glacier, crystals might start as tiny grains a few millimeters across and grow to several centimeters over years. In deep polar ice, crystals can reach sizes larger than a grapefruit. This coarsening process affects how ice deforms. Coarse-grained ice flows differently than fine-grained ice. Time itself changes ice texture. Crevasses form when ice deforms too quickly. While ice normally flows plastically, it can fracture if stressed rapidly. When a glacier flows over a steep bedrock step or around a curve, the surface ice must stretch faster than plastic deformation allows. The ice cracks, forming crevasses, deep fractures that can be hundreds of feet deep. These crevasses gradually close as the glacier continues flowing and pressure pushes the ice back together. But new crevasses continually form in areas of high stress. The ice is simultaneously flowing and fracturing, transforming through both brittle failure and plastic deformation. It's solid and fluid at once. Rain on snow creates rapid transformation. When rain falls on a cold snowpack, the liquid water carries heat into the snow. This heat energy can cause significant melting and metamorphism in a short time. The rain also fills air spaces, increasing snow density and changing its structure. Heavy rain on snow can transform a low-density powder snow into dense, consolidated snow in just hours. This rapid change affects the snowpack's stability and can trigger avalanches. Climate change is increasing rain on snow events in many mountain regions, altering the seasonal cycle of snow accumulation and melt. Sublimation removes snow without melting. Water can transition directly from solid ice to water vapor without passing through the liquid phase. This happens constantly on snow surfaces, especially on sunny, windy days when humidity is low. In high mountain environments and polar regions, much more snow is lost to sublimation than to melting. The snow simply evaporates into the dry air. Sublimation preferentially removes molecules from crystal tips and ridges, contributing to the rounding of snow crystals. Over time, sublimation can cause significant snow loss. A snowpack can shrink noticeably without any melting occurring. Fresh powder snow can be as much as 90% air by volume, making it one of nature's best insulators. As snow settles and compresses, air gradually escapes from the spaces between crystals. The snow becomes denser, heavier. Eventually, when buried deep enough and compressed long enough under the weight of new snow above, these air spaces close off completely. They become bubbles trapped in solid glacier ice. These bubbles preserve samples of ancient atmosphere, allowing scientists to study what Earth's air was like thousands of years ago. The trapped air tells stories of past climates. Surface hoar forms when water vapor deposits directly onto snow. On clear, cold nights with high humidity, water vapor in the air freezes directly onto the snow surface, creating feathery crystals that look like frost. These delicate crystals can grow several inches tall overnight, creating a beautiful, glittering layer. But when buried by new snowfall, surface hoar becomes a weak layer in the snowpack because the crystals are loosely bonded. Like depth hoar, buried surface hoar is a common cause of avalanches. Beautiful transformation sometimes creates hidden danger. Ice appears to flow smoothly, yet acoustic measurements reveal something quieter. When scientists placed sensitive microphones on deforming ice, they discovered that plastic flow happens through intermittent whisper, like bursts. Dislocations within the crystal structure move in cascades, with periods of rapid motion followed by quiet periods. These dislocation avalanches are power law distributed, meaning most deformation occurs in a few large events rather than many small ones. This discovery changes how scientists model glacier flow and ice sheet dynamics. Ice moves in gentle jerks and pauses, not continuous smooth flow. So yes, snow and ice are already revealing their transformative nature by showing us that frozen water never truly freezes into permanence. Every snowflake that lands begins changing immediately. Every glacier constantly reshapes itself. Every ice crystal responds to its environment by rearranging molecules, growing, shrinking, changing form. We're beginning to see that frozen is a misleading term. Ice is better described as very slowly fluid. And this continual transformation happens at every scale, from individual molecules to continent-sized ice sheets. Change is ice's fundamental character. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside. Trillions of organisms working in silence. Heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. You are a complete ecosystem, diverse, self-balancing. Now we continue. Water's unique properties make ice transformation possible. Unlike most substances that contract when freezing, water expands. This expansion occurs because the hexagonal structure of ice has more space between molecules than liquid water does. This unusual behavior means ice is less dense than water, which is why it floats. Ice cubes bob on the surface of your drink. Icebergs drift across oceans. But it also means ice is less structurally stable than most frozen materials. The molecules in ice remain relatively mobile, even well below freezing point. This molecular mobility allows continuous rearrangement, bonds breaking and reforming, crystals growing and shrinking, shapes evolving. Water's peculiar nature makes ice unusually dynamic for a solid material. The very properties that allow life to exist in frozen lakes also allow ice to transform constantly. Impurities in snow affect how it transforms. Pure snow metamorphoses differently than snow containing dust, pollen, or pollution particles. These impurities can act as nucleation sites where crystal growth begins, or they can inhibit growth depending on their chemical nature. Recent research shows that even small amounts of impurities significantly alter snow metamorphism rates and patterns. Desert dust blown onto mountain snowpacks from as far away as the Sahara causes faster melting because the dark particles absorb more solar radiation than white snow. Sea salt in coastal snow changes how crystals bond to each other. Volcanic ash creates distinct layers. Snow is rarely pure, and these impurities actively participate in transformation processes, leaving their chemical signatures behind. Glaciers flow faster in their centers than at their edges. Friction with valley walls and bedrock slows ice at the glacier's margins, creating drag forces that resist motion. Meanwhile, the center, free from friction, moves faster downstream. This differential motion causes the ice to deform internally, stretching in the middle section and compressing at the sides. If you placed markers in a straight line across a glacier, within a year, they would form a curved line downstream, with the center markers having traveled much farther than the edge ones. This pattern of motion creates internal stresses that continuously reshape the ice from within. The glacier's shape, its width, depth, and curve, determines its flow pattern in predictable ways. Basal ice, the ice at a glacier's bottom, behaves very differently than surface ice. This ice experiences tremendous pressure from the weight of hundreds or thousands of feet of ice above. It's often at its melting point due to geothermal heat from Earth's interior rising through the bedrock below. Recent measurements in Taylor Glacier, Antarctica, showed that about 60% of the glacier's surface velocity comes from deformation in just a 15-foot thick basal layer. Even at -18 degrees Fahrenheit, this compressed basal ice deforms rapidly. The combination of high pressure and relatively warm temperature makes basal ice dramatically softer than the cold, brittle ice at the surface. Pressure, more than temperature alone, controls transformation here. Fresh powder snow is remarkably light, with a density as low as 30 to 50 kilograms per cubic meter, or about 3 to 5% the density of pure ice. Over days and weeks, as crystals bond together, and air spaces shrink through settling and metamorphism, density increases to perhaps 150 to 300 kilograms per cubic meter. After years of compression deep in glaciers, as the snow transforms completely into glacier ice, it approaches the density of pure ice, about 917 kilograms per cubic meter, a tenfold transformation from airy powder to solid ice. The journey from snowflake to glacier ice is a journey of increasing density and decreasing air, happening gradually over years or decades. Rounded snow grains bond together more strongly than fresh snowflakes. As pointed features disappear through metamorphism, the contact points between adjacent crystals grow larger and stronger. This process, called sintering, gradually welds individual crystals into a more cohesive mass, like tiny welds forming between touching grains. The snowpack gains structural strength over time if temperature remains relatively stable. However, this strengthening competes with weakening processes like depth hoar formation in temperature gradients. The balance between strengthening, sintering, and weakening recrystallization determines snowpack stability, information crucial for avalanche forecasting. Snow scientists dig pits to examine these layers, testing bond strength by hand. Transformation isn't just about shape. It's fundamentally about the strength of connections between crystals. Wind-packed snow creates surface crusts through mechanical transformation. Wind breaks crystals into smaller fragments, while simultaneously pressing them together with tremendous force. The mechanical action of wind-driven crystals colliding also causes slight melting at grain contacts due to friction heat, which then refreezes immediately, cementing grains together into a solid mass. The resulting wind crust can be strong enough to support your weight, while the unconsolidated snow beneath remains soft and loose. These wind features, called sastrugi, create wave-like patterns on snow surfaces that reveal prevailing wind directions. The patterns can be several feet tall in Antarctica. Wind sculpts snow like an invisible landscape artist working in frozen water. Crystal orientation affects how ice deforms under stress. Ice crystals have a preferred slip direction along their basal plane, the flat hexagonal face you can visualize. When many crystals align with their basal planes oriented in the same direction, the ice mass deforms more easily in that particular direction, like a deck of cards sliding. This alignment typically develops as glaciers flow over time, with crystals rotating into preferred orientations through the deformation process itself. Polar ice cores show distinct layers with different crystal orientations, each layer recording different past flow conditions and stresses. The ice develops a fabric, an internal texture that guides and influences its future deformation in predictable ways. Glaciers that contain liquid water, even tiny amounts distributed along grain boundaries or concentrated at the base, flow notably faster than completely frozen glaciers. Recent laboratory experiments revealed something surprising about temperate ice. Ice containing small percentages of liquid water deforms almost linearly with stress, quite different from the nonlinear behavior of cold ice. This helps explain why some ice sheets can accelerate suddenly when surface meltwater reaches the glacier bed through cracks and channels. The presence of even 1% liquid water by volume can increase flow rates by factors of 10 or more. Water is ice's lubricant at the molecular scale. Recrystallization changes ice texture without any melting. In warm ice or ice under high stress, existing crystals break down and new crystals grow in their place through a solid-state transformation. Large, strained crystals become many small, unstrained ones, releasing stored energy. Or many small crystals merge into larger ones, depending on temperature and stress conditions. This dynamic recrystallization continuously modifies ice structure in flowing glaciers. Similar to how metals recrystallize when heated and worked by blacksmiths, the ice is constantly rebuilding its internal structure from within, maintaining mechanical integrity while flowing downhill over centuries. Snow metamorphism slows dramatically as temperature decreases. At -40 degrees Fahrenheit, transformation proceeds at a glacial pace compared to snow at 20 degrees. The cold effectively locks molecular motion into slow motion. This is why polar snow can preserve delicate crystal structures for extended periods. The frigid temperatures slow molecular movement to a crawl. In the warmest snow, near 32 degrees Fahrenheit, metamorphism accelerates dramatically. A few degrees difference in temperature can change transformation rates by factors of 10 or more. Temperature is the throttle, controlling the speed of transformation. Ice sheets deform differently at different depths, creating distinct mechanical layers. Near the surface, ice is cold, brittle, and relatively stiff. At intermediate depths, ice deforms primarily through the slow creep processes we've been exploring. At the very base, where pressure and temperature are highest, and meltwater may be present, ice can flow much more easily. The ice sheet essentially has layers with different mechanical properties stacked on top of each other, all flowing at different rates. Understanding this vertical structure is crucial for modeling how ice sheets respond to climate warming. Firn is the intermediate stage between snow and glacier ice. This granular, partially consolidated snow undergoes active metamorphism. Not quite snow anymore, but not yet solid ice. Air spaces between crystals are still connected to the atmosphere through tiny passages, but compression is gradually closing them off. In polar regions where temperatures stay below freezing year-round, snow might remain as firn for decades before finally becoming true glacier ice. In warmer climates with seasonal melting, the transition takes just a few years. Firn represents transformation in progress, caught between two states. Recent research revealed that ice shelves are more sensitive to stress changes than previously thought. Studies across Antarctic ice shelves using satellite measurements of flow velocity suggest the flow law exponent should be 4 rather than the traditionally used value of 3. This mathematical detail has profound implications. It means ice shelves respond more dramatically to changes in stress. A small increase in driving stress produces a proportionally larger increase in flow rate than older models predicted. This sensitivity matters for predicting how ice shelves respond to warming oceans and thinning. Water content dramatically affects how snow transforms. Dry snow metamorphoses primarily through vapor transport, sublimation, and deposition, moving molecules through air spaces. Wet snow containing liquid water transforms much faster because water facilitates molecule migration between crystals. The liquid preferentially melts convex surfaces and refreezes in concave areas, rapidly rounding crystals through what scientists call melt-freeze metamorphism. Just 1% liquid water by volume can accelerate transformation by orders of magnitude. The presence of liquid makes snow metamorphism proceed in hours, what would take days or weeks in dry snow. If you're still awake, still listening to Earth's frozen secrets, that means curiosity hasn't fully rested yet. And that's okay. Take a gentle breath. Feel the weight of your body on the bed, grounded like ancient ice. We're wandering through nature's quiet wisdom together. And we'll keep going, slowly. Beneath the surface, quiet, energy moves constantly. Every transformation of snow and ice involves energy exchange with the surroundings. When snow metamorphoses from low-density powder to denser packed snow, energy is released as bonds form, warming the surrounding air slightly. When ice melts, it absorbs energy from its environment, about 144 BTUs per pound of ice. That's why ice in a drink cools the liquid, absorbing heat as it melts. When water vapor deposits directly onto ice crystals to form frost or snowflakes, energy is released into the atmosphere. These energy exchanges affect local temperature and humidity in subtle but real ways. Snow and ice transformations are part of Earth's energy cycle, constantly exchanging heat with the atmosphere in an invisible dance of thermodynamics. Snow acts as insulation that protects the ground beneath from extreme cold. Even a foot of snow can keep ground temperatures significantly warmer than air temperatures, sometimes 20 or 30 degrees warmer. This happens because snow contains so much air trapped between crystals, and air is an excellent insulator when held still. As snow metamorphoses and densifies through the winter, its insulating properties change. Fresh, fluffy snow insulates better than dense, packed snow because it contains more air. This thermal protection affects how deeply the ground freezes in winter, influences when plants emerge in spring, and determines whether small mammals can survive beneath the snowpack. Subnivean spaces, hollow areas beneath the snow, become winter homes for voles and shrews. Snow creates hidden ecosystems. Avalanches represent catastrophic transformation. When weak layers in a snowpack fail under stress, from new snow loading, warming temperatures, or a skier's weight, an entire slope of snow can transform from a solid mass into a flowing fluid in seconds. The avalanche converts gravitational potential energy into kinetic energy with devastating speed. Snow that was stable moments before becomes a destructive flow capable of moving at highway speeds. The transformation from solid to fluid happens because bonds between snow crystals break simultaneously across a large area, a cascading failure. Understanding how snow transforms over time helps avalanche forecasters predict where and when this sudden change from solid to fluid might occur. Lives depend on understanding these transformations. Ice cores reveal past atmospheric composition because air bubbles trapped in ice contain samples of ancient atmosphere. But scientists must account for how the ice has deformed since the air was originally trapped. The bubbles themselves change shape as ice flows over millennia. Originally, spherical bubbles become elongated in the direction of ice flow, stretched like taffy. By analyzing bubble deformation and comparing it with ice crystal fabrics, scientists can reconstruct the ice's flow history and correct for how deformation affected the core samples. The deepest ice cores from Antarctica have been significantly thinned by flow. What was originally a 100-year layer might now be compressed into just a few meters. Understanding transformation is essential to reading the ice archive correctly. Climate warming is profoundly changing snow metamorphism patterns in mountain regions worldwide. More frequent melt-freeze cycles create more ice layers in snowpacks. Earlier spring melting changes the duration of snow cover by weeks. These changes affect water resources because mountain snowpack acts as a frozen reservoir, storing winter precipitation and releasing it gradually through spring and summer. Altered transformation patterns mean altered timing and amount of spring runoff, affecting agriculture, hydropower, and drinking water for millions of people. The Himalayas, Andes, Alps, and Rockies are all experiencing shifts in snow dynamics. The shape-changing snow affects entire river systems and the ecosystems and human communities that depend on them. Permafrost, permanently frozen ground, is transforming in Arctic regions as Earth warms. As temperatures rise, ice within permafrost begins to melt, causing the ground to subside and deform. Recent measurements show accelerating rock glacier movement across the European Alps as internal ice warms and deforms faster. Ground that was frozen for thousands of years is thawing within decades. These changes threaten infrastructure built on permafrost. Buildings tilt, roads crack, pipelines bend. The thawing also releases carbon dioxide and methane stored in frozen soils, gases that were locked away during past ice ages. The frozen ground is becoming unfrozen and unstable, transforming landscapes and climates simultaneously. Ice fog forms through rapid transformation of vapor to solid ice. in extremely cold air below -30 degrees Fahrenheit, common in polar regions and continental interiors in winter, water vapor from human breath, vehicle exhaust, or open water can freeze directly into microscopic ice crystals suspended in air. No liquid phase occurs. Vapor becomes solid instantly. These ice fog events demonstrate how quickly transformation can occur when conditions are right. The crystals are so small, they remain airborne indefinitely, creating ghostly frozen clouds that reduce visibility to near zero. Cities in Alaska and Siberia experience ice fog regularly in winter, a visible manifestation of phase transformation. Rime ice forms when supercooled water droplets freeze instantly on contact with surfaces. When freezing fog or cloud droplets carried by wind-strike objects, tree branches, power lines, mountain peaks, they transform from liquid to solid in milliseconds. This creates feathery white deposits that grow into the wind direction. Mountain weather observers have recorded rime formations several feet thick building over days, entirely coating structures. The transformation happens so fast that the water doesn't have time to spread before freezing, creating intricate frozen sculptures. It's transformation through collision, liquid becoming solid through sudden contact with any surface cold enough to initiate freezing. Black ice on roads demonstrates hidden transformation. When thin layers of water freeze on pavement, they become nearly invisible, transparent ice that shows the dark road surface beneath, creating a dangerous illusion. This deceptive form happens through quiet transformation, as temperatures drop after rain or snow melting. The water spreads thin across the pavement, freezes clear without air bubbles, and creates surfaces where friction nearly disappears. Drivers encounter what looks like wet pavement, but behaves like an ice rink. The water transforms from liquid to solid so smoothly that no visible change marks the transition, only the sudden loss of traction. Halfway through our journey now, the answer is emerging clearly. Snow and ice change shape because molecular bonds between water molecules can break and reform easily near the melting point. Temperature, pressure, humidity, impurities, wind, sunlight, and time all influence how and how fast these bonds rearrange. Transformation isn't a flaw in ice's structure. It's ice's fundamental nature responding continually to its environment. Every snowflake, every glacier, every ice crystal is always in the process of becoming something slightly different than it was moments before. Ice teaches that permanence is illusion, change is reality. Notice this halfway point in our journey. Breathe slowly, feel the cycles. Ice forms and melts, snow falls and transforms. Water moves from sky to ground, to stream, to ocean, to sky again. All are circles, cycles, endless movements. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal rhythm. You don't need to hold on to anything. Let everything unfold in its perfect order, like water molecules silently rearranging in ice crystals. Unhurried, unresisting, simply existing. We're almost there now. Ice transformation happens simultaneously at every scale. At the molecular level, individual water molecules break bonds and form new ones in patterns dictated by temperature and pressure. At the crystal scale, individual snowflakes and ice grains change shape through sublimation and deposition. At the snowpack scale, layers compress and weak zones develop. At the glacier scale, entire ice masses flow downhill. At the ice sheet scale, continent-sized bodies of ice spread outward under their own weight. And remarkably, each scale influences all the others. A molecular rearrangement, repeated in trillions of crystals, produces measurable glacier motion. Glacial flow, creates stresses that cause molecular rearrangements. The scales are interconnected in an elegant hierarchy of transformation. Glaciers write their history in their deformed structure. Folded layers, tilted strata, and crystal fabrics tell stories of past flow that glaciologists read, like geologists read rock formations. A fold in an ice layer indicates the glacier flowed around an obstacle. Stretched layers show where the glacier accelerated. Vertical crystal orientations near the bed indicate strong shearing. The deformation patterns reveal where the ice came from, how fast it flowed, what stresses it experienced over centuries. Scientists photograph these structures in ice tunnels carved into glaciers. The ice becomes an archive, a library written in transformations. Each fold and fracture is a sentence in ice's autobiography. Fresh snow on a calm day has its own distinctive acoustic quality, or rather, its own silence. Snow absorbs sound waves exceptionally well because of all the air spaces between crystals. These tiny air pockets trap and dampen sound energy, creating the hushed quality of a fresh snowfall. But as snow metamorphoses and consolidates, its acoustic properties change noticeably. Old, crusty snow sounds different underfoot than fresh powder. It crunches and squeaks rather than softly compressing. In spring, sun-crusted snow creaks under your weight. You can hear transformation in how snow responds to footsteps and to sounds traveling through it. Each stage of metamorphism has its own voice. Spring snow goes through dramatic daily cycles of transformation. Cold nights allow crystal bonding to strengthen as temperatures drop. Warm, sunny days melt the surface snow into a slush. The melted surface refreezes overnight, creating a hard crust. By afternoon, it becomes slushy again as the sun returns. This daily rhythm of freezing and melting accelerates transformation remarkably. Spring snow can change from hard enough to walk on to soft enough to sink into, and back again twice each day. Skiers time their descents for corn snow, the brief window when the surface has softened but not yet become too slushy. Spring demonstrates transformation's daily tempo. Lake ice transforms differently than glacier ice. When water freezes on a lake surface, crystals grow downward into the still liquid water below, forming columnar structures aligned vertically. These columns can be quite large, several inches across and feet long. The ice develops in distinct layers that record different freezing events. Clear ice forms from direct freezing of water. White ice forms when snow on top melts and refreezes. Layered ice alternates between clear and cloudy bands. Each layer tells a story of temperatures and snowfall. Ice fishers learn to read these layers, knowing that clear ice is stronger than white ice of the same thickness. Frost heave demonstrates ice's transforming power in soil. When water in soil freezes, it expands about 9%, pushing soil upward. Repeated freezing and thawing gradually moves rocks to the surface. This is why farmers find new rocks in their fields each spring. In Arctic regions, frost heave creates patterned ground, polygons, circles, and stripes of sorted stones that look almost artificial. The transformation from liquid water to solid ice in tiny soil pores generates enough force to lift buildings, crack pavement, and sort stones by size. Ice's expansion during transformation becomes a geological force. Ice lenses form in soil through gradual water migration toward freezing fronts. As soil freezes from the surface downward, unfrozen water deeper in the soil is drawn upward toward the freezing zone by capillary forces and pressure gradients. This water freezes into distinct layers, ice lenses, that can be inches thick, lifting the soil above them. The process continues as long as water can migrate through unfrozen soil below and temperatures stay below freezing above. These ice lenses cause significant frost heave. Roads buckle, sidewalks crack. Transformation builds layers powerful enough to deform infrastructure. Antarctic blue ice areas reveal ancient ice through wind ablation. In certain regions of Antarctica, katabatic winds, gravity-driven winds flowing downslope, constantly remove surface snow faster than new snow accumulates. This exposes glacier ice that originally fell as snow thousands of years ago. The blue color comes from ice's preferential absorption of red wavelengths of light while reflecting blue. Walking on blue ice feels like walking on ancient time. Each step takes you deeper into history, farther back in years. Blue ice areas show transformation's long timescale made visible. Sea ice transforms differently than freshwater ice. Salt water freezes at lower temperatures, about 28 degrees Fahrenheit, rather than 32 degrees for fresh water. When ocean water freezes, salt is partially excluded from the forming ice crystals, creating brine channels and pockets within the ice. These channels allow continued water circulation through the ice. Sea ice is more porous, more permeable, and more dynamic than lake ice. It breathes with tides and currents. Organisms live within the brine channels. Sea ice hosts entire ecosystems in its transforming structure. Needle ice forms when soil water freezes and grows upward into the air. On cold, clear nights, ice needles can grow several inches tall, lifting soil particles on their tips like tiny frozen pillars. By morning, they melt, depositing soil in slightly new positions. Repeated over many nights, needle ice can sort soil particles and move them gradually downslope. You might see fields covered with these delicate ice needles on winter mornings, forests of tiny ice crystals growing from earth, transforming soil structure grain by grain. Hoar frost on windows creates beautiful patterns through sequential transformation. Water vapor deposits directly on cold glass in branching crystal formations that grow and spread. The patterns reflect temperature gradients and air currents near the glass. Each window's frost pattern is unique because local conditions around each point on the glass are slightly different. The frost grows like a garden overnight, starting from nucleation sites and branching outward. By morning, entire windows can be covered with intricate ice ferns. Warmth from inside gradually transforms the frost back to water. Pressure melting under ice skates makes skating possible. The pressure from your weight concentrated on the narrow blade lowers ice's melting point very slightly, creating a thin water layer between blade and ice. You glide on this microscopic water film. When pressure releases behind the blade, the water refreezes immediately. Skating is transformation enabling motion. Solid to liquid, to solid again in fractions of a second. The ice doesn't know it's being transformed. It simply responds to pressure and temperature changes. Glacial striations on bedrock record ancient ice transformation into landscape-shaping force. As glaciers flow over rock, debris frozen in basal ice scratches parallel grooves into the bedrock below. These grooves show flow direction from thousands or tens of thousands of years ago. The patterns reveal how ice sheets transformed the landscape through grinding motion over millennia. Even after the ice melts, the scratches remain, permanent records of temporary ice, transformation's signature written in stone. Icicles grow through repeated cycles of melting and freezing. Water drips from the tip, but some freezes before falling, adding a thin layer. Each freeze adds growth. Over hours or days, icicles lengthen and thicken. Their shape records the temperature and water flow history during growth. Fast dripping makes long, thin icicles. Slow dripping makes thick, short ones. Icicles are frozen records of transformation tempo. Ice clocks measuring winter's rhythm in visible form. Ice transformation connects to water cycles on every continent. Mountain snowpack stores winter precipitation and releases it gradually as summer meltwater. Polar ice sheets contain 70% of Earth's fresh water. Glaciers feed rivers that sustain billions of people. Sea ice influences ocean currents and climate patterns. The water moving through these frozen forms connects atmosphere, land, and ocean in cycles spanning days to millennia. Understanding ice transformation means understanding planetary-scale water movement. Snowdrifts, sculpted by wind, show transformation through removal. Wind erodes snow from exposed areas and deposits it in sheltered zones, creating dunes and drifts. These features shift and reshape with each wind event, sometimes dramatically overnight. The snow surface becomes a fluid landscape responding to invisible forces. Drifts can bury vehicles, block roads, or create towering cornices on mountain ridges. Wind-driven transformation can move more snow than snowfall itself. Glacier mills, vertical shafts where surface meltwater drains into glaciers, shift position as surrounding ice deforms. What starts as a straight vertical hole becomes curved and tilted as the ice flows. The holes record ice motion like tree rings record growth. Each season's melting carves new channels that then deform. Some mills spiral deep into the glacier, following the ice's internal flow patterns, becoming liquid pathways through solid ice. Sun cups form on snow surfaces through differential melting. Small initial depressions catch more sunlight, warm faster, melt deeper, and grow larger. This positive feedback creates a dimpled surface pattern across entire snowfields. The snow transforms into an egg carton texture through solar-driven selective melting, responding to micro-topography. Each cup is slightly different, reflecting local variations in density and crystal structure. The pattern emerges from simple physics. Recent observations show glacier acceleration in response to surface meltwater reaching the bed. Water finding its way through crevasses reduces friction at the glacier base, allowing faster sliding over bedrock. But this response is complex, sometimes short-lived, as drainage systems develop and evolve. Ice motion couples to water in intricate, transforming relationships. Some glaciers speed up dramatically during summer melting, then slow again as efficient drainage channels form. Snow crystals in clouds can transform during their initial formation. A crystal might start growing as a plate at one altitude, then fall into a different temperature zone and switch to columnar growth, creating unusual hybrid shapes before ever reaching the ground. Some snowflakes show distinct sections recording different growth phases, a central column with plate-like arms extending from the ends. Their atmospheric biographies written in ice. We're seeing the unity of transformation across forms and scales. Ice crystals at the nanometer scale follow the same thermodynamic principles as glaciers at the kilometer scale. The same molecular properties that allow a snowflake to transform in minutes allow a glacier to flow over centuries. Water, near its freezing point, exists in a state of dynamic equilibrium, perpetually responsive to its environment. This isn't chaos, it's order, expressing itself through continuous change. Ice transformation reveals fundamental truths about how matter responds to energy, pressure, and time. In a world where nothing truly stands still, ice shelf carving represents dramatic transformation. Solid ice shelf becoming floating icebergs in moments. The ice doesn't change form immediately, but its relationship to land, ocean, and gravity transforms instantly. Connection becomes separation. Supported becomes floating. Stable becomes mobile. These carving events can be enormous. Icebergs the size of cities breaking free. The sound travels for miles, a thunderous announcement of transformation's power. Seasonal snow cover extent has decreased measurably over recent decades in many regions. The transformation from winter white to summer brown happens earlier each year. Spring arrives sooner. This changes how much sunlight Earth reflects and how much water is stored temporarily as snow. Transformation patterns themselves are shifting, responding to planetary warming. The rhythm of seasons is changing. Ancient ice contains volcanic ash layers that have been stretched and folded by flow. These marker horizons, originally deposited as horizontal layers from atmospheric fallout, now curve and undulate through the ice. The ash itself doesn't transform, but ice deformation transforms their geometry. Scientists use these ash layers as traces, following their curves to understand flow patterns through time. By this point, the answer is clear. Snow and ice change shape because water molecules, unlike most substances, remain mobile and responsive even in solid form. The hydrogen bonds linking them together are weak enough to break and reform constantly, yet strong enough to maintain structure. This balance creates a solid that flows, a frozen material that transforms. Change is written into ice's molecular architecture. You might be feeling tired now. That's perfectly fine. Breathe slowly. Notice the simplicity. Most matter, from a grain of sand to a mountain, is mostly empty space. Atoms are mostly empty space between nucleus and electrons. Even ice is more emptiness than substance. So let go. Let all pressure, all worry dissolve. Like ice crystals slowly sublimating into air, present one moment, gone the next, without struggle. We'll continue with the final facts. In this final section, we move beyond mechanics to meaning. The transformation of snow and ice whispers something profound about existence itself. Nothing remains unchanged. Even the seemingly permanent glacier flows. Even the most delicate snowflake, preserved in photographs for eternity, was already transforming the moment after its image was captured. The frozen world is not frozen at all. It's dancing slowly. Perhaps permanence is the illusion we impose on a reality that's always becoming. Perhaps change is the only constant, and acceptance of this truth brings peace. Consider how snowflakes form in clouds you cannot see, transform during a fall you might not notice, and change shape on the ground while you sleep. Most of their transformation happens beyond human observation. The changes occur in darkness, in silence, without witness. Yet they happen anyway, following physical laws that care nothing for observers. The universe transforms whether we watch or not, whether we understand or not. Consciousness is not required for change to occur. Change simply is, independent and eternal. Glaciers teach patience through their transformations. They change shape over decades, centuries, millennia. Ice that fell as snow before humans built pyramids still flows slowly toward the sea in Greenland, still transforming after 4,000 years. The glacial pace is actually profound wisdom. It's the rhythm of geological time. Perhaps there's deep knowledge in transformations so slow it's invisible to a single human lifetime. Not all change requires speed. Some truths reveal themselves only to those who watch for generations. Yet some ice transformations happen in instants. An avalanche releasing, an iceberg carving, pressure melting under a skating blade. The same substance that demonstrates geological patience also shows split-second dynamism. Ice contains both timescales within itself. It transforms slowly and suddenly. It's patient and dramatic. These seeming contradictions coexist peacefully. Perhaps opposites are just different expressions of the same fundamental nature, responding to different conditions. Ice teaches that contradictions can be true simultaneously. Water is the only common substance that exists naturally in all three phases: solid, liquid, gas, at Earth's surface temperatures. Ice, water, and water vapor constantly transform into each other in endless cycles. This fluidity between states makes Earth's water cycle possible. It makes weather patterns. It makes climate. It makes life itself possible. The transformation of frozen water isn't just a curiosity. It's essential to the planet's functioning and to existence as we know it. Looking at old photographs of glaciers from a century ago beside recent photos reveals transformation we rarely witness directly. The ice has retreated miles, changed shape profoundly, thinned dramatically. What looked eternal proved temporary. This isn't just about climate change. It's about recognizing that even mountain-sized masses of ice respond to conditions. Nothing, no matter how massive or ancient, exists beyond change's reach. Size offers no immunity from transformation. Children building snowmen understand something profound without knowing it. They know snow's malleability instinctively. They pack snow to make it stronger, add water to make it stickier, work with its transforming nature. They're collaborating with metamorphism, shaping snow during its transformation. Play and science intersect. The child and the glaciologist study the same phenomenon at different scales with different vocabularies, but equal wonder. Both honor transformation's creative possibilities. Indigenous peoples living with ice developed deep knowledge of its transformations over millennia. The Inuit had dozens of words for different types of snow and ice, each describing specific transformation states and their implications for travel, hunting, and survival. This vocabulary recognized subtleties that science is only now measuring precisely with instruments. Traditional knowledge and modern science both honor the complexity of transformation, approaching it from different perspectives toward shared understanding. Imagine watching a glacier transform in time-lapse, centuries compressed into minutes. You'd see it breathing with seasons, flowing like a slow river, advancing and retreating with climate cycles. The solid Earth itself appears fluid when time accelerates. Perhaps solidity is a matter of perspective, an illusion created by our brief lifespans. What seems permanent at one time scale flows visibly at another. Time reveals transformation. The transformation of snow and ice connects to every season's rhythm. Fall's first frost, winter's accumulation, spring's melting, summer's remaining patches in shadows. The cycle repeats annually, yet each year differs slightly. Ice and snow mark time's passage while demonstrating time's circularity. The same process returning, never quite identical, always changing. They measure both linear time and cyclical time simultaneously. Understanding ice transformation has changed how we see stability itself. We've learned that what appears permanent, snowpack, glaciers, ice sheets, actually flows, changes, responds continuously. Stability is temporary. Equilibrium is dynamic, not static. Even the ground beneath our feet, when frozen, is still moving imperceptibly. This knowledge doesn't diminish ice's majesty. It enhances appreciation by revealing hidden complexity. Artists have long been drawn to snow and ice's transformative beauty. The way ice crystals catch light, how snow softens harsh landscapes, the blue depths of glacial crevasses. Art recognizes what science measures, that transformation itself creates beauty. Change becomes aesthetic. The impermanence enhances rather than diminishes appreciation. Beauty intensifies when we know it's temporary, still transforming. Each winter snowfall offers renewal. Old snow transforms and melts away. New snow arrives pristine, covering what was. The cycle suggests possibility. The transformation allows fresh starts. Winter's white blanket covers autumn's decay, offering visual and metaphorical reset. Spring's melt reveals transformation's completed work and initiates new growth. Endings become beginnings through transformation. There's something meditative about watching snow fall, each flake descending on its unique path, each landing and beginning its transformation journey. The steady accumulation, the gradual landscape change. Snow teaches presence. It's happening now, this moment, this quiet transformation blanketing the world while we watch in stillness. Transformation as meditation, as peaceful acceptance of change. Understanding ice transformation changed multiple sciences: climate science, hydrology, glaciology, planetary science, all emerged partly from studying how frozen water changes. Curiosity about changing shapes led to understanding Earth's systems, water cycles, climate patterns, and even conditions on other planets. One question about transformation opened worlds of knowledge. Ice became a teacher of planetary processes. The human relationship with ice is ancient and intimate. Ice preserved food before refrigeration. Ice made surfaces slippery for transportation. Ice formed barriers and created bridges across rivers. Understanding its behavior meant survival for millennia. Modern life insulates most of us from this immediate relationship, but ice transformation still matters profoundly. It affects water supply for billions. It influences sea level for coastal communities. It shapes climate patterns globally. The old relationship continues, though we notice it less in our temperature-controlled environments. Ice still shapes human destiny. Consider that ice cores drilled from Antarctica contain ice over 800,000 years old, compressed from snow that fell during dozens of ice ages. Yet even that ancient ice has transformed continuously throughout its existence, flowing, compressing, recrystallizing. Age doesn't mean unchanging. The oldest ice on Earth is still creeping slowly, still deforming under pressure, still responding to physical laws. Even 800,000 years is not long enough to freeze ice into permanent stillness. Transformation outlasts ages. Lakes freezing in winter demonstrate transformation we can witness firsthand. The surface changes from rippling water to still ice over hours or days, sometimes overnight. Sound changes, water's gentle lapping replaced by ice's sharp cracking and deep booming as it expands and contracts with temperature. One form becomes another, audibly and visibly. You can stand on water, walk across surfaces that were liquid days before. The transformation is complete enough to bear weight. Ice hotels, carved fresh each winter from snow and ice in places like Sweden and Canada, embrace transformation completely. Artists create intricate spaces knowing they'll melt with spring's warmth. The impermanence is integral to the art, not separate from it. Guests sleep in rooms that will disappear within months. Beauty intensified by its temporary nature. Transformation acknowledged as medium and message. The hotels celebrate ice's changing nature, rather than resisting it. Perhaps the deepest truth isn't that snow and ice change shape, but that change itself is universal. Ice makes change visible, slow enough to study with scientific instruments, fast enough to observe within human lifespans. It's a teacher demonstrating what everything does. Mountains erode, stars evolve, galaxies spin. Everything transforms given enough time. Ice reveals this truth at scales we can comprehend, making the abstract concrete and visible. The real transformation isn't in the ice at all, it's in our understanding. We changed from seeing ice as frozen and static to recognizing it as dynamic and responsive. Our perception transformed through paying attention, through measuring carefully, through watching patiently. The ice was always transforming. We're the ones who changed, learning to see what was always there. Understanding itself is a form of transformation. And in that transformation of understanding, we recognize ourselves. We too change constantly. Cells replacing themselves, thoughts shifting, bodies aging, perspectives evolving. Ice's transformation mirrors life's transformation. Both are continuous becoming, never fully finished, always in process. Perhaps ice teaches that trying to freeze ourselves in place, to resist change, creates suffering. Accepting transformation creates peace, flow, rather than freeze. So the answer to why do snow and ice change shape leads to a deeper answer. Because change is reality's fundamental nature, not an aberration from some imagined permanent state. Resistance to change creates friction and suffering. Accepting transformation as natural creates harmony. Ice flows with the stresses it experiences rather than breaking. Perhaps that's wisdom, yielding without collapsing, changing without losing essence. Look at snow outside your window now, or imagine it. Know that even as you watch or picture it, the snow is transforming, molecules rearranging themselves, crystals growing or shrinking, bonds breaking and forming, change happening invisibly in apparent stillness. The quiet holds transformation, silence contains motion, stillness is full of subtle change when you look closely enough to see. The frozen world teaches that nothing freezes forever. Everything flows eventually, even ice, even time, even us. Change is not the exception, change is everything. The snowflake falling is already becoming something else. The glacier flowing is reshaping itself continuously. Understanding ice's transformation means understanding that permanence was always illusion. There is only this eternal becoming, this endless transformation, this beautiful, inevitable change. And so, our quiet journey through ice and snow comes to a gentle close. We've traveled from tiny molecules dancing in crystal lattices to continent-sized ice sheets flowing toward the sea, discovering along the way that frozen means constantly transforming. From snowflakes forming in clouds to glaciers carving valleys, we've glimpsed how water becomes ice, becomes water again, endlessly cycling, forever changing, never truly still. Snow and ice remind us that change is not something that happens to things. Change is what things are. Much of this transformation happens in silence, in darkness, in depths we cannot see, in timescales beyond human perception. They teach us patience in their slow glacier crawl, and drama in their sudden avalanche. Without transformation, water would be trapped in one state forever. By pausing to notice, we glimpse the extraordinary in the ordinary. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about how water cycles through clouds, rain, ice, streams, and oceans. Everything connected, everything returning, everything flowing. You are part of that flow, that cycle, that eternal return. Let your entire being dissolve into the rhythm of nature, into the breath of the earth, into stillness. Prepare for deep sleep. No boundaries left, only peace. If these calm stories from Earth helped you breathe a little easier, passing them along could help another tired soul drift into rest. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of transformation to fade now, like snowflakes melting on warm ground, leaving only gentle moisture behind. Let your breathing deepen. Let your body feel heavier, as if snowfall is gently covering you with a soft white blanket of warmth and stillness. If sleep comes, let it carry you like water flowing downhill, smoothly, inevitably, into a realm where time dissolves and nothing needs to change because everything already is perfect. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, snow will still be transforming somewhere. Ice will still be flowing in glaciers you'll never see. Crystals will still be growing in clouds above while you sleep below. But tonight belongs to stillness. Rest well, quiet scientist. And remember, transformation is not the opposite of peace. Transformation is peace expressing itself through time. Dream deeper with bedtime science. Good night.